Tammy Leung is doing her PhD thesis in the printed team of the ICAS group since 3 years ago in the framework of a research project called ELECTRON. Her background is in material science, and her expertise has been really valuable for the project goals. ELECTRON project aims at developing sustainable electronics, sensors, and batteries by establishing renewable, abundant, and cost-efficient electronic materials together with new manufacturing processes for a reduced environmental impact. The main objectives are not only related to the use of biodegradable and eco-friendly functional materials and substrates, but also on the sustainability of the whole process to reduce its embodied energy and environmental impact. The work presented today is part of the activities developed by Tammy during the last years and will contribute to the development of a more sustainable electronics, especially in disposable and transient applications. Okay, so Tammy, it's your time.
Sure. I'm going to share my screen now, and hopefully things will appear correctly. Okay. Sorry, I don't know if you can see this window. Okay. So thank you, Eloy, for that introduction, and thank you for inviting me today to talk about my current research project on shaping the future of electronics with biodegradable materials and alternative manufacturing processes. Today, I hope to familiarize you about the future of electronics, which I believe is transient electronics, and the motivation behind my project. Additionally, I will talk and review different layers of building a transistor with biodegradable alternatives and what my contributions have been thus far concerning the substrate as well as the ink development. As inkjet printing is an integral part of my project, I will review the basics behind inkjet printing and the sintering techniques that must accompany it in order to create low temperature conductive films. From here on, I will introduce a new metal salt-based ink that will produce these conductive films using different strategies. And lastly, I will briefly talk about the semiconductor layers that we will potentially be used to complete our transistor. And finally, I will also conclude with a brief summary and future work. The future of electronics, I believe, is transient electronics. This is a term that was first coined by John Rogers in 2013, which basically describe electronics that degrade after usage. Currently, there are two types of transient electronics. The first is biodegradable, which can degrade through chemical means, which means by water or when placed in an acidic solution, or through microorganisms such as bacteria or fungi. The other is bioresorbable electronics, which can be implemented into a host and will start to degrade on contact. However, this will have negligible effects on the host itself. And the reason for the existence of transient electronics is that it's a response to the excessive amount of electronic waste that is produced every year. And this is due to specifically our consumer mentality to buy and throw away electronics, as well as the manufacturing processes behind producing them. This results in chemicals that can leach out into the environment, further polluting it. And for this reason, we need to develop more sustainable systems that reduce this waste through the implementation of biodegradable materials. What must be noted here is that the substrate already accounts for 90% of electronic components, which therefore theoretically replacing this can be considered already biodegradable. However, we would like to go further in order to make sure that every single layer that itself is completely biodegradable. And this will be achieved with inkjet printing functional inks that will be developed onto biodegradable substrates to build these electronic components or transistors. A transistor itself is basically a stack of layers which increase in complexity when compared to functionality. So this can be built from the ground up, starting with a substrate and includes a combination of conductors, insulators, and a semiconductor layer. If for future reference in this presentation, we won't go over the insulation or the dielectric layer, as the substrate can be reused for this layer itself. These layers also, the substrate itself can be made of biodegradable materials, which pertain to natural and synthetic polymers, papers, amongst others. So here we tabulated different types of biodegradable materials that were eliminated based on very strict criteria. The first of which was extremely important was requiring that the biodegradable substrates be able to handle curing temperatures above 120 degrees C. For this, I specifically tabulated the glass transition temperature for each of the considered substrates, or the glass transition temperature here is in reference to the temperature at which the substrate can decompose or begin to soften. Specifically, there will be multiple generations for the transistors, where the first generation we will consider just the changing the biodegradable substrate and building organic typical components on top, where again the biodegradable substrate once again must be able to withstand 120 degrees C. Just with this specific restriction, we were able to eliminate the majority of the substrates. However, some cellulose derivatives, silk fibrillene, and other standard materials remained. In terms of the second generation, where we will start to include biodegradable inks, which could and will be UV or room temperature curable, allowed the introduction of PVA as a substrate as well. In terms of when considering all of the materials here, we see that silk fibrillene is sort of a standout material, as it offers the best combination in terms of the working temperature as well as biodegradability. If the substrate itself was not commercially available, we chemically synthesized it, or in terms of silk, for example, this was extracted. Because a planar substrate was necessary for the inkjet printing process, different coating techniques such as solution casting and spin coating were explored. And once each chosen material was fabricated, they were then subjected to different materials characterization techniques. The first of which is differential scanning calorimetry, where both the glass transition and melting temperature were determined. And once again, the restriction here is that they must be able to withstand a temperature of at least 120 degrees C. Unfortunately, all of the chosen substrates here did not meet this requirement, as biodegradable substrates tend to be thermally unstable. Another very important factor in the building of a transistor is also the roughness of the substrate itself, which can be carried on to the subsequent layers deposited above. Therefore, this value must be minimized. In terms of the substrates chosen here, silk fibrillene showed the lowest at approximately 1 nanometer, while others such as papers or cellulose alternatives here showed the highest. Additionally, the sodium carboxyl methyl cellulose was eventually eliminated as a material because of its extreme reactivity to water and its extremely high roughness. Therefore, all the rest of the remaining subjects were used for further testing. Again, because all of the chosen substrates contained a glass transition temperature that was lower than 90 degrees C, we were then forced to adapt to be able to place a conductive layer on top that was within this temperature range. And this again this was done with conventional materials, as this is part of the first generation of transistors, and we accomplished this using inkjet printing and plasma sintering itself. Inkjet printing was chosen here because it has the ability to be able to deposit different types of inks and metals onto the surface. And with the addition of plasma allows for lower sintering temperatures as compared to thermal heating techniques. In this case, we actually specifically chose oxygen plasma for the sintering process because this can be found in a standard laboratory and does not require things such as high vacuum to operate. So it operates at atmospheric temperature. Inkjet printing itself is an additive printing technique that deposits droplets one by one onto any given substrate, which can create patterns down to tens of microns. It functions through the use of a piezoelectric actuator that when a voltage pulse is applied to the reservoir walls, contracts and then releases the ink through the nozzle itself. Simultaneously, the print head laterally scans the substrate, printing the pattern line by line. The advantages of this technique include the fact that any type of substrate can be printed regardless of whether or not it is flexible or rigid, and it allows for a very low waste of ink in the end. However, most of the disadvantages include the fact that there are many restrictions on the inks that have the ability to be printed here. Meaning, for example, the nanoparticles and nanoparticle inks cannot be larger than 300 nanometers, as it is likely to clog the print head. So for this reason, the inks themselves must be adapted to inkjet printing in order to print consistently. And still today, nanoparticle inks remain the most dominant and commercially available ink specifically for inkjet printing. The development of such inks are actually a very complex process, which requires the chemical synthesis of nanoparticles and an addition of the additives, capping agents, and coal solvents and binders in order to stabilize the nanoparticles, as they are more prone to agglomeration due to their high surface energies. This in turn further increases the sintering temperatures and therefore limits the use of thermosensitive substrates. Typical post-treatment is through thermal heating, which results in films that are stacked, separate nanoparticles, and are extremely porous, where you can only see sort of a slight necking of the nanoparticles together. On the contrary, a new type of ink that I want to introduce here is the metal salt decomposition inks, which is a simple formulation that requires just a metal precursor, water, and solvent. This simplified formulation helps to reduce the sintering temperature, but also allows for the novel introduction of novel sintering techniques, such as plasma, which again allows for a much more smoother, uniform film, and allows also for the nanoparticles to combine or coalesce together. The table here shows a direct comparison of the advantages and disadvantages of each ink. So there seems to be sort of a steady evolution where the complexity of the formulation is reduced while also being able to incorporate thermal sensitive substrates as this becomes more and more important in flexible electronics. Simultaneously, the cost of the ink is also greatly reduced, while there is an increase in the number of metallic films that can also be formed. Even amongst these improvements or changes, we see a similar conductivity of a range of good to excellent. And this only further shows that metal salt decomposition inks are superior to nanoparticle inks. So it was previously shown in literature that argon plasma could be used to demonstrate a wide range of metal films that are dependent on their reduction potentials. Specifically, how this works is the plasma itself dissociates the metal salt into cations and anions. So the metallic cations are reduced to its elemental state, while the anions here, such as chlorine, are removed in vacuum. The combination of this type of ink with plasma allows for a facile thin film development on low temperature and non-conventional substrates. And the energy here that is needed to convert the salt ink is solely based on the ionic reduction potential of the metallic cation, where a positive value actually indicates the ease at which you can do this. So taking this into account, we chose highly positive metals, which here are gold, silver, and platinum, and to see how they would convert using oxygen plasma itself. Firstly, for the gold film, we were able to deposit successfully on a wide range of substrates, ranging from the typical polymers, papers, and fabric, which resulted in different types of opaque gold films. These films themselves varied in roughnesses depending on the substrate that it was first deposited in. So it could go from very smooth to extremely rough, as again, the roughness is carried on for the substrate below. The films themselves could be sintered as little as 5 minutes for a very thin film, or up to 20 minutes in order to obtain an optimal highly conductive film. We see that specifically through the deposition onto non-planar substrates such as the abaca paper and polyester textile, that the film was formed extremely conformally, which is something that has never been seen before. These films, again, were sintered at 35 degrees C or below, which makes it a low temperature process itself. And specifically, again, when looking at the different substrates, we were able to determine the relationship between the sheet resistance and the surface roughness, which roughly follows a linear or is directly proportional. That is, the sheet resistance increases as the surface roughness increases. Polyester here was sort of an outer layer. However, polyester fabric itself is actually a polymer, so the ink stays on the surface and is available to be converted, therefore explaining the lower sheet resistance that you see here. Something else to note is that the gold film that was deposited onto PET showed columnar grains, symbolizing the polycrystallinity of the film. And so this was verified using XRD, which showed excellent matching diffraction peaks across the surface, where any additional peaks were contributed by the PET substrate below. Additional analysis was done using SEM and EDX, which showed some chlorine contamination on the surface, which is seen as salt crystals. This means that the plasma process itself did not fully remove the salts because of the low power that was actually applied. Additionally, the surface roughness was around 116 nanometers and showed conductivities for this film up to 10 to the 5 Siemens per meter, all of which is more or less on par with those deposited on nanoparticle inks. The platinum film itself showed reduction within 6 minutes using the oxygen plasma and had conductivities up to 10 to the 4 Siemens per meter. Under SEM observation, we see that the film itself was highly porous and showed a lamellar microstructure itself. The porosity itself is attributed to the removal of the chlorine ions, which when comparing the gold and platinum shows 1.5 times more chlorine. So this roughness that you can see on the surface contributes to the appearance of the film as well as the lower conductivity. Again, another verification that we always do is using XRD to see the purity of the platinum film that was created. And we see here that there are decently matching peaks. However, there are other peaks that we have yet to explain, but again, some of them are attributed to the platinum substrate below. And the reason for this circular pattern that you see in the fully developed films is that we discovered that through EDX that there is chlorine, there was still the presence of chlorine on the surface, which means that plasma itself was removing the chlorine in different areas at different rates. So this is why you see sort of a circular pattern. The development of the silver film is very similar to the platinum films, where the fact that you can see very quick recrystallization of the ink, especially if it was developed, a very thin layer was developed or was printed, meaning that the crystallization pattern actually was completely seen and remained even during the conversion process. Additionally, because silver is more prone to oxidation, the application of oxygen plasma quickly oxidized the surface. This again, under SEM observation, we see that this silver film also showed a lamellar structure here with porosity. And at least with the EDX analysis, we see that the nitrogen was removed from the surface. However, XRD showed a completely different story where the diffraction pattern didn't match many of the references. Therefore, the impurity of this film, there was impurities in this formation of this film. Because of these results, the ink was no longer used for further experimentation, and it is well known that silver nanoparticle inks are already available and optimized for inkjet printing. This is sort of a summary of all of the inks that we were able to convert. An additional aside is the fact that we actually had tried other types of inks like copper and tin. However, they had sort of a similar problem as the silver, as they tend to oxidize quickly. And the reason for this is that the copper and tin, they both have extremely negative reduction potentials. Therefore, adding more electrons to these cations tends to recrystallize and create, again, this pattern that we saw previously, instead of actually converting it to its elemental form. For the other inks, such as gold and platinum, we were able to control the oxidation with the oxygen plasma and saw reproducible results across the way. Previous studies we had showed used argon plasma itself to be able to reduce a much greater amount of metallic films. However, they saw temperatures of 150 degrees C or above, meaning that, again, thermosensitive substrates could not be used in this case. And once again, this is not something that we saw in our with our substrates and this technique itself. So once everything, the formulation and the optimization, well, once everything was optimized with the respective inks, we were able to make different types of applications, such as conductive tracks and a glucose biosensor. So the gold conductive tracks are printed onto a polyester substrate, which showed excellent tensile and compressive strains. Again, there was excellent adhesion during testing, where we never saw delamination of the film from the surface, as it continued to be conductive beyond 10% strain. This has important implications in the wearable electronics industries, as electronic textiles themselves must be able to withstand at least 10% strain. Another application we had here is the development of a fully inkjet printed glucose biosensor. This biosensor consisted of a 3-electrode configuration where the gold was used as the counter and working electrode, and the rest, such as the conductive tracks, pads, and the reference electrode, were printed with the silver nanoparticles. However, due to the limited working area, only glucose detection was found in the millimolar range, which is appropriate for blood glucose detection in particular. As sensors, sensors that are typically printed with nanoparticles tend to have poor adhesion and often need an adhesion layer. So, and compared to our specific sensors, there was no delamination of the gold film seen, making it a potential to be used as a reliable, flexible device. Excuse me. So the previous reducing mechanism that we were discussing previously was based on the use of plasma conversion. However, we discovered sort of an alternative process that could be used that produces an equally conductive film at room temperature. Here, the reducing agent is the substrate itself, which must contain numerous hydroxyl groups in order to initiate the reaction. In this case, we used PVA, which was able to form a conductive film within 11 days. Sorry, excuse me. At room temperature, without needing any external sintering technique. For a more instantaneous result, sintering temperature can be increased and forms a similar layer within 30 minutes. As the idea of transient electronics is still a relatively new idea to the scientific community, one of the least developed layers here is the degradable semiconductor. Here I will provide a brief introduction about the different types of biodegradable semiconductors in existence, which is 3 different types. The first is inorganic, which include silicon, zinc oxide, and molybdenum oxide. However, these conventional semiconductors require high temperature annealing in order to form the layer. And this is especially difficult to incorporate into our transistors. Another type is naturally occurring, such as beta carotene and malic chitosan nanofibers. However, both tend to have extremely low carrier mobilities. Additionally, there are a myriad of dyes that can be used in order to simulate or to function as a semiconductor layer. However, they are not biodegradable. A new type of semiconductor is a polymer type, where they took the degradability of DPP, which is a specific dye, and used conjugated polymers in order to develop semiconductors with decent carrier mobilities. Unfortunately, these experimental semiconductors are not commercially available and are still uncomparable to standard semiconductors. So in conclusion, we have demonstrated that transient electronics can be accomplished by replacing common or typical materials with biodegradable alternatives for the substrate, dielectrics, and semiconductors. However, these biodegradable materials always comes with restrictions, specifically with the temperature stability, and therefore we need to use low temperature sintering techniques that are able to develop these films on top. Sorry, I don't know why that changed. We demonstrated a new type of ink called this metal salt decomposition ink, where we created low temperature conductive films, such as gold, platinum, and silver with good conductivities. And unfortunately, again, because there is only a handful of semiconductors that are considered biodegradable, this is one of the last layers that we have yet to place into our devices. Currently, we are finishing up sort of the first generation transistor that was discussed previously, where we would like to develop an ionic PVA gel, which in this case can act as the dielectric layer and the substrate. Simultaneously, we are starting the development of the second generation transistor, which uses molybdenum and zinc biodegradable nanoparticle inks onto our biodegradable substrates. So far, these inks show a decent resistance. However, the surface roughness is extremely high compared to the previous inks that were discussed. For this particular transistor for the second generation, we are considering a gate bottom contact configuration that is pursued, along with the addition of a biodegradable substrate, which will be placed above in order to create a fully biodegradable transistor. Thank you very much for your attention. And if you have any questions, feel free to ask now, or if you prefer, you can contact me later with my email. And here are my references as well.
Thank you, Tammy. Thank you. It was a very thorough summary of transient electronics and your work.
Thank you.
And I think we now have a pretty good idea of what you do. So we open up the time for questions. If anybody has anything they want to ask, feel free to do it now, or put them on the chat and we will read them, whatever you want. We have Tammy here, we have also Eloy, I think he's still here. And we have time for a couple of questions.
Hello, this is Luis. Tammy, thank you very much for your presentation.
Yes.
I think you said that for some layer you try to avoid some artificial sintering, and you let them sinter naturally, and it took like 11 days.
Yes.
Is this something acceptable for these applications, or which will be a reasonable time limit for a layer that sinters naturally in order for being compatible with an
Right.
industrial process or certain productivity, so to say?
I mean, I'm not sure if I can answer this question correctly, but yes, specifically the self-sintering ink does take a longer period of time, but if for a manufacturing process, we can obviously increase the sintering temperature. And this layer can be developed within just 30 minutes itself. So for more practical applications, the creation of this layer can be done quickly.
Thank you, Tammy.
No problem.
Yes, thanks, Luis. No, today, for example, silver commercial inks requires of 30 minutes of sintering in a conventional oven. So it's still not, let's say, maybe really interesting, especially when thinking in printed electronics in roll-to-roll processes, because roll-to-roll is expected, I mean, it's a continuous manufacturing, so it's expected to, let's say, use some kind of technology faster than, let's say, conventional oven, because 30 minutes is too much. Okay, but well, the idea here was more, let's say, to try to reduce or to avoid using, let's say, sintering that requires too much energy. But well, for sure, 11 days, it's not. It's just, let's say, an academic game. No, I mean, that it doesn't have any sense.
You commented that semiconductor materials are not ready yet in general.
Correct.
This is because they're still, you know, in a process of being developed, or there are significant difficulties for achieving them. Is there any particular important problem that is preventing obtaining such semiconductor materials?
I mean, in general, there aren't very many degradable semiconductor materials in existence. So developing them like these polymer types is something that I would say not many groups have been pursuing thus far. The most recent publication actually was on 2019. So again, I think that the scientific community in general is just lagging behind, as there hasn't been so much concentration, and because the carrier mobilities are so low, it also makes it not as attractive as, say, using the standard conventional semiconductors that we're used to today.
Mm-hmm. Thank you.
Yes, no problem.
Thank you, Luis. Okay, any other question? Any volunteer? Okay, if there isn't anything else, we will wrap it up for today. You have Tammy's contact, and you can see her in the corridor, so you will be able to find her other days. Thank you for the presentation, Tammy, and thank you, Eloy, for the introduction. Thank you, everyone who attended. The session will be available on YouTube. That's it for today. Well, next week is Easter, so have a good week if you are off, and have a good weekend. Thank you. Bye.
You too. Thank you.
Bye-bye, everyone.